Imagine whenever we describe images, we need to specify numerical values for every corner of the image. Instead of describing the attributes of the image content, like color, shape, or texture, we need to spit out pixel values to represent the image. This is actually how images are represented in computers. Every point in the image needs to be assigned a numerical value. Images are represented as a collection of pixel values, ranging from 0 to 255. So whenever we want to process an image, such as changing it to grayscale, sharpening, or blurring the image, we need to process each and every pixel. If we have a dataset of 2028 by 28 images, we need to process 4.7 million pixels. But here's something to think about. If we randomly dropped 100 pixels from an image, we'd likely still recognize its content. This hints that pixels might not be the fundamental units of image understanding. So could there be smarter, more efficient ways to represent images in computers? Decades ago, Hinton and Salakhutdinov thought about the same question. They came up with an architecture that takes in high-dimensional data and compresses it to low-dimensional codes. But what do we mean by dimensions? And how can dimensions be reduced to represent the same data? Dimensions are the number of axes or features we need to represent our data. Think of it this way. If you have an image with thousands of pixels, each pixel could be considered a dimension in the original data. A latent space reduces this to a smaller set of dimensions where each dimension represents some abstract feature or combination of features, like edges, shapes, or textures in an image. These dimensions may not be directly interpretable in human terms, but are mathematically derived to encode the data efficiently. The number of dimensions in a latent space is a design choice. Fewer dimensions means more compression, but might lose important details. More dimensions retain more information, but can make the model harder to train or interpret. The autoencoder has three main components. Let's start with the encoder. The encoder compresses the input into a smaller, dense representation, called the latent space or bottleneck. The encoder's job is to take a high-dimensional input, like an image, and distill it down to a lower dimensional representation that captures the most important features. For images, this means going from, say, a 28 by 28 pixel grid to a compact vector of, say, 32 numbers. It's like summarizing a book into a few key sentences, but instead of words, we're dealing with patterns in data. The encoder starts with one or more convolutional layers. Each layer applies a set of filters, small windows like 3 by 3 grids, that slide across the image. These filters detect features like edges, corners, or textures. Filters are tiny pattern detectors. One filter might catch horizontal edges by giving high values when it sees a sharp change from dark to light across a row. Another might spot vertical edges. The weights in these filters are learned during training. As the filter slides or convolves over the image, it computes a dot product between the filter and the patch of pixels it's looking at. This produces a feature map, a new grid showing where that feature appears in the image. But how are filters learned? The filter values, or weights, start as random values. They need to be tuned so the autoencoder can compress the input and reconstruct it accurately. Updating weights is how the network learns which features, like edges or shapes, are worth capturing. This happens through backpropagation and gradient descent, guided by a loss function. The loss function is how we quantify how bad the reconstruction is. A common choice is the mean squared error. This measures the average squared difference between original and reconstructed pixels. The latent space is the compressed, structured representation of the input data produced by the encoder right before it gets handed off to the decoder. It's often called the bottleneck because it's much smaller than the original input, like squeezing a big image into a tiny vector. This compact form is the essence of the data stripped down to its most important features. The latent space acts as a bridge. The encoder compresses the input into this low-dimensional form, and the decoder tries to rebuild the original image from it. The latent space is the key to what makes autoencoders useful. It forces the network to summarize the input, discarding noise and redundancy. Those features encode meaningful patterns, like edges or shapes learned during training. It's also a way to represent complex data, like images or audio, in a simpler interpretable form. Similar inputs map to nearby points in the latent space. Big differences map further apart. This smoothness comes from the network generalizing patterns across the dataset. The decoder is the second half of an autoencoder. After the encoder squeezes the input into a compact latent space vector, the decoder's job is to reverse that process, turning those few numbers back into something as close as possible to the original input. It's essentially the decompression step, aiming to rebuild the image. The decoder mirrors the encoder but in reverse, while the encoder uses convolutions and pooling to shrink the data spatially and extract features. The decoder uses operations to expand the latent space back to the original size. The decoder learns a mapping from the latent space to the input space. Its filters and dense layer weights decide how latent dimensions translate to pixel patterns, while the encoder builds features, from edges to shapes for instance. The decoder unpacks them from shapes to edges to pixels. There are lots of use cases of autoencoders. Autoencoders can compress data into a lower dimensional latent space and then reconstruct it. This makes them useful for tasks like storing huge-sized data and reconstructing it back for processing. By learning the normal patterns of a dataset, autoencoders can detect outliers or anomalies. For instance, in cybersecurity, they can identify unusual network traffic, or in manufacturing, they can flag defective products based on deviations from normal sensor data. Variational autoencoders, a specific type, are widely used to generate new data samples similar to the training set, such as creating realistic images, faces, or artwork. They're foundational in generative AI alongside models like GANs and diffusion models.